Welcome to How to Succeed in ECE Without Really Trying. I'm Dr. Linda DeBrenner, and in this video, I'm discussing the operational amplifier. Okay, let's talk about an actual device. So a very common type of op-amp is called the 741. It's a small integrated circuit, looks just like this. It's got four legs on each side. Just a little tip. We number our pins starting here 1, 2, 3, 4. On the other side 5, 6, 7, 8. Okay, and we know where to start numbering because on integrated dual inline packages like this, we have a little divot here on the left side, or in our case here, a little dot right on that top of the circuit. And so that's how you know how to orient it. The dot or the divot goes to the left. And here's showing the pinouts, okay? Um, when you're using operational amplifiers or any kind of a circuit, you actually need to provide power. So on this circuit, we add a a plus voltage and a minus voltage. Different circuits have different voltages and different voltage levels are needed. Okay, and this is actually the circuit that's implemented by that 741. Now, you don't need to know how to analyze this circuit, fortunately, okay? But what we have is a bunch of transistors. Each of these is a transistor, and it built a bunch of, and then we have resistors and other things. So you can see where the inputs are coming in from the other side. So this is what's going to happen in practice. If you wanted to build a circuit with an op amp, you'd buy something like a 741 and connect it up. And again, you would only need to know what pin goes where. The gain for this particular op amp is on the order of 10 to the 5th or 10 to the 7th, and that's typical for other op amps as well. Okay, so I told you don't have to analyze this whole circuit. Let me tell you how we're going to do it instead. Okay, so we're not going to use that circuit diagram. We're going to make an ideal assumptions about how op amps work. Okay, first thing we're going to assume, okay, is that input current is equal to 0. So IN equals 0. The second thing we're going to assume is that the input voltages are equal. That means that V minus is equal to V plus. Okay, it's important to note that that's only true when we have negative feedback. So just remember that V minus is equal to V plus only when there's negative. You can only make that assumption when they have negative feedback. So this is going to give us a model where we can use these simple rules, right? That IN is equal to 0 and V minus is equal to V plus. And that's going to make analyzing the circuits much easier. Okay, so let's do three good examples. They're classic examples. You will in your career are likely to encounter more or one or more of these. Okay, and I will go through them in general. So we'll have inverting amplifiers. So the voltage will get flipped on the output. Non-inverting amplifiers. So the voltage remains the same direction. If it's positive, it will remain a positive. If it's negative, it remains negative, but it still amplifies. And then we also have something we call voltage followers or source followers. Those are isolating circuits that can be used for various purposes. Okay, so let's just take each of these in turn. First, we'll consider an inverting circuit. Here's a simple circuit. We have the operational amplifier right here, represented by a triangle. Has an inverting input marked with a minus, a non-inverting input marked with a plus. Has two inputs, okay, and the output V out. So then I've put this in in a whole circuit with resistors. This source input, I've written it like this, but we have in the past seen it written more like just a voltage source. Okay, Vs of t. Sometimes you will see people put a little squiggle in the middle to emphasize the idea that it's a time varying signal. But we've got Vs of t, so we know it's time varying. Okay, so no matter how you write it or draw the picture, it's going to give you the same results. Okay, so let's do some KCL. So what we're going to do is we're going to sum some currents at the node. Okay, now let's remember what our assumptions were, right? So we assumed that V plus was equal to V minus, and we also assumed that IN plus is equal to IN minus, which is also to be a 0. We usually just say that as IN is equal to 0. But I wanted to emphasize to you that the IN at the plus side is equal to 0, and the IN at the minus side is also equal to 0. Okay, so what we're going to do is we're going to sum the currents at that node. And we're going to do that just like we've done with all the circuits we've looked at that did not have op amps. So we're going to look at each of those in turn. From here to here, so we can just say Vs minus V minus over R. Okay, Vs minus V minus over R, that's this current. This current that was entering. So we're going to sum entering today. Okay, and then we have V out minus V minus over RF plus 0 equals 0. So there's our nice simple equation we would get. That Vs over R plus V out over RF is equal to 0. We could write our KCL equations at the other nodes, but they're not helpful. So just write them at that node in the inverting node there. Okay, remember our assumption that V minus was equal to V plus. And also we noticed that V plus is connected directly to ground, so that means V minus is equal to ground. So that's why I was able to get rid of the extra terms in there. So this gives us, when we take this equation, rearrange it, V out over Vs is equal to minus RF over R, and we define that to be the gain. Okay, let's make a little notes. We will notice that the input resistance is Vs over Is, which is equal to R. And ideally, you'd want that input impedance to be very large so that you wouldn't load the source. And you can see that from the gain equation, G will approach 0 as Rn approaches infinity. So we want Rn to be large, but as it gets very large, that drives our gain down. So that's not what we really want, okay? But on the other hand, we can set our gain to be whatever we want the gain to be. So that is a wonderful thing. So we have some competing interests there in what we want that Rn to be. Let's look at another circuit. Again, this is a circuit with an op amp. We label our inputs clearly, minus and plus. We do not have to put the minus on top and the plus on the bottom, so always look to see how it's labeled. Okay. Again, I've shown just the VN there on, let's zoom in a bit. The VN is just shown going in between terminals. We often do not draw in the source just because it clutters up our diagram. So I want you to feel comfortable looking at them both ways. Again, similarly, we don't usually draw a load resistance, we just write V out. Okay, so we're going to do the same thing we did a minute ago. We're going to use KCL. We're going to remember that IN is equal to 0 at both the inverting and non-inverting inputs. Sometimes we call them terminals. Okay, also remember that V minus is equal to V plus. Now this circuit might seem a little harder, and that's okay. We'll deal with it. Okay, so we're going to do KCL again. We look in here. This voltage is going to be equal to this voltage, right? The two V minus and V plus are equal. So we need to figure out what V plus is. Well, the current going into that terminal is 0, right? Going in. So if I is equal to 0, the voltage drop across that resistor R is also 0. And that means that V plus is equal to Vn. So there's that written down. And we also know that V minus is equal to V plus, so V minus is equal to Vn. Now, we will also write an equation at this node that I just turned blue, right? Okay, so I have V minus minus V out over RF plus V minus minus 0 over R1 plus 0 equals 0. Let me show you where those all came from. So V minus minus V out over RF, that's current leaving there. I think in the previous example I had them entering the node, but it doesn't matter. It always works either way. So V minus minus V out over RF plus V minus minus 0 over R1, and then the current going in here is 0, so we'll say it's equal to 0. So we substitute in for V minus is equal to Vn. We get Vn minus V out over RF plus Vn over R1 is equal to 0. We can rearrange our terms. There's some algebra there. And we end up with V out over Vn is 1 plus RF over R1. So clearly this means that the gain G will be greater than 1. Ideally, you'd like to be able to set it less than 1 sometimes, so it would actually attenuate. We would still call it a gain, but a gain less than 1 reduces the voltage. So this, circuit's a little bit limited in that the gain has to be greater than 1, but it's a useful amplifier, okay? And also notice that the input resistance to that circuit is infinity. Rn is equal to 0, and that's because there's no current flow. So that is a really wonderful result. Okay, so now let's look at a third kind of amplifier. So we've looked at an inverting amplifier and a non-inverting amplifier. So we're going to look at a special case of a non-inverting amplifier. So what we're going to do is, again, we're going to write our equations. We remember that In is equal to 0, V minus is equal to V plus. And now we're going to write our equations. If we plug in RF is equal to 0, we end up with the gain is 1. You could write the equations over again, or we can just use our previous result. In either case, you're going to end up with a gain of 1. What this means is that V out is equal to Vn. Now, initially, you might think that's not useful at all, but what we actually have in practice is that consequence means that the input voltage and the output voltage are going to be the same, but you've actually isolated the output from the input. So the purpose of the isolating amplifier is not to actually provide gain, but instead to isolate the source from the load. And we do this quite a bit often. This means that no current is drawn from the source. It's useful for many, many different kind of fixed sensors. And if you have problems with inverting or non-inverting amplifiers of different kinds, you can use this in combination with an inverting amplifier or non-inverting amplifier to provide isolation from the load. And then you could have an inverting amplifier to follow with a gain less than 1 if you wanted, whatever you need to do. So the purpose of an isolating amplifier is to isolate the load from the source. So we introduced the idea of a operational amplifier and covered 3 common configurations: the inverting amplifier, the non-inverting amplifier, and an isolating amplifier. In practice, you will often see sensors interfaced using one of these fairly standard approaches.